Hello everyone, and thanks for watching the fourth video of this series. In the last video, we studied some aspects of semiconductors or intrinsic semiconductors. In particular, we derived an expression for the electron hole concentrations and their relationship with the Fermi level. We observed that as we increase the temperature, these concentrations rise exponentially, and what's more, we studied a way to relate this with an observable, with something that we can measure in the lab. We studied the connection between carrier concentration and conductivity. Today, we are going to take our semiconductors to the next level with the miracle of doping, a technique that consists of inserting impurities randomly in the crystal lattice of a pure semiconductor. To this aim, let's start this video by reminding the concept of conductivity in intrinsic semiconductors. It is the constant of proportionality between the generated current and the field applied. And I would like to emphasize here that the two terms involved are proportional to the carrier concentration. If you remember, we could increase the carrier concentration and therefore the conductivity by increasing the temperature. Today, we are going to do it as well, but artificially, by replacing atoms in the crystal lattice by other atoms that can effectively release or trap electrons. But before that, I'd like to make a couple of comments first. First, in general, very often, logarithmic scales are much more suitable than linear scales to interpret our output, especially when the output combines different orders of magnitude. Here, for example, I know that at room temperature, the concentration is about 1.6 10 to the 16th per cubic meter, but it looks like zero because the last part of the graph is saturating the scale. In contrast, if we use a logarithmic scale in the y-axis, we can actually put things in perspective. For example, look at this point here. At about 170 Kelvin or minus 100 Celsius, there is one electron and one hole per cubic meter, which is a ridiculously small concentration. Second, doping is not about adding charge to the material. Every time you replace a silicon atom by a pentavalent impurity, like phosphorus, you add one proton and one electron to the system. As we will see, this extra electron has a natural tendency to travel across the crystal lattice, leaving behind a frozen positive charge. And the same goes for a trivalent impurity like boron. These types of impurities have a natural tendency to trap electrons, which results in a hole that is able to travel across the crystal lattice, leaving behind one electron with an extra negative charge, which is fixed in the lattice. So despite extrinsic semiconductors having impurities, they all are neutral. Now, let's move our discussion to the momentum space. This is the band structure of intrinsic silicon. Normally, the number of impurities is not enough to modify the dispersion. Its only effect is to add or donate field electronic states within the energy gap. When we add donor impurities, these states normally are very close to the bottom edge of the conduction band. Here, ED stands for the energy of those donors. As a result, the Fermi level is displaced to the midpoint between ED and the bottom edge of the conduction band. And when the material is at room temperature, all these electrons in the donor impurities occupy the conduction band, leaving behind fixed holes that don't move and therefore do not participate in the transport properties. The same goes when we add impurities that enable electronic occupation from the valence band. In this case, at room temperature, all electrons in the valence band occupy all these states, leaving behind holes in the valence band that are now free to move and fix electrons around the impurities that are frozen. Okay, now let's study the concentration of electrons in n-doped silicon as a function of temperature. This graph shows a comparison between intrinsic silicon and doped silicon with phosphorus. Did you see any difference? 3, 2, 1. Okay, me neither. And that's because we're using a linear scale. We need to use a logarithmic scale. Here, we see that the logarithmic concentration of pure silicon is inversely proportional to minus the temperature. But electron-doped silicon seems to have a different behavior, seems to have 3 temperature regimes. Okay. The first range of temperature is the so-called impurity range. As temperature increases, impurities are ionized and electron concentrations in the conduction band skyrocket. Obviously, at some point, this trend reaches a plateau where pretty much all impurities are ionized. This is where the second range starts, also known as the exhaustion range. And it is characterized by a saturation regime, where no matter how much you increase the temperature, the concentration is kept constant. The third range, the intrinsic range, is characterized by a number of electrons that are promoting directly from the valence band, outnumbering the electrons coming from the impurities. In this range of temperatures, both extrinsic and intrinsic semiconductors have the same concentration. However, normally, we are interested in what happens at room temperature, where impurities have the potential to increase the concentration by several orders of magnitude. And with the concentration, conductivity also increases, because this formula, it is still true. The only difference is that now electron concentration overwhelms the whole concentration, leaving behind an expression that effectively depends entirely on the features of the conduction band. Okay. Now it's time for an example, for an exercise. Here, we are asked to get the conductivity from the mobility of the intrinsic concentration, from the mobility and the intrinsic concentration. So I'm giving you a couple of seconds for you to pause the video. Okay, for those who solved it, congratulations. And for those who just want to enjoy the show, we just need to remember the concept of mobility, which is the parameter that tells us how quickly an electron can move through a metal or semiconductor when pulled by an electric field. It is therefore the constant of proportionality between the drift velocity and the external electric field. Now, if we multiply both sides by the elementary charge and by the electron hole concentration, and then add them up, all we have left is an alternative definition for the conductivity. Plug in some numbers, we get 5.08 10 to the minus 4 ohms minus 1 meter minus 1. Okay, bear this in mind, because here it comes the second part of the exercise. We dope our material with phosphorus or boron, and we want to know the conductivity. Now, I would like to draw your attention to the sentence, assuming all dopants are ionized, because this is a typical sentence in exercises of semiconductor physics. And it is basically reminding us that we are in the exhaustion regime. As before, I give you a couple of seconds to pause the video and plug some numbers in the previously derived formula for the conductivity. I'd like to emphasize that even though both electrons and holes participate in the conductivity, there is roughly 1 hole per million electrons, which basically explains why we can safely drop the second term. As for the second part, we apply the very same formula, keeping in mind that this time there is 1 electron per 10,000 holes. And if you ask my calculator, this is the answer you get, 0.77 ohms minus 1 meter minus 1. Okay, today we learn how we can boost the performance of semiconductors with the miracle of doping. It consists of adding impurities that either give electrons to the conduction band or trap electrons from the valence band, giving rise to holes. In both cases, the conductivity increases by several orders of magnitude. But so what? Why is this so relevant in modern technology? Well, precisely that question will be the topic of the next and last video of this series. Until then, goodbye.